So good morning, everybody. My name is Ramon Amela, and I'm researcher at Rootstock Labs, as he has been just nicely presenting me. And I will be explaining how BitVMX works in a simple way and giving some hands-on examples. So this will be a little bit the outline of the talk. I will be explaining a little bit about the Bitcoin context, then do a recap of some nice concepts that are applied in BitVMX to pass afterwards to show how the NRI research on-chain works and how we perform the error resolution on-chain. Finally, we'll do a hands-on when we will show these two concepts in real examples in mainnet, testnet, and Winternitz. So, the Bitcoin context. As you may know, if you have ever coded in Bitcoin, Bitcoin is not like Ethereum or other blockchains that have smart contracts and are really expressive. In Bitcoin, we have stateless scripts, so we don't have the concept of database or state or the capacity to pass variables from one transaction to the other. We have very limited amount of opcodes, meaning that we are not even able to multiply or concatenate or do meaningful things, so we are extremely limited. There's no transaction introspection, so we cannot say where the money from one transaction will go or limit where the money come from. So we just have some conditions to spend a UTXO, and then we don't know anything from the transaction inside the script that will free these funds. Finally, we have signed arithmetic operations with at most 32 bits. That it's 4 bytes. That is super small. Taking all this into account, some people have done some research to kind of stretch a little bit the script and try to overcome all these limitations. So I'm talking about the connectors, the Winternitz one-time signatures, and the chain hashes. At first, I will explain all these concepts because they are really important on the continuation. So what is a connector? As you may know, Bitcoin is a UTXO-based blockchain. So basically, we have a transaction and a block. And in this block, we put transactions. And these transactions have several outputs. So we can identify an output by the transaction ID and the index of the output. If we want to spend this output, we need to give to the blockchain the conditions that fulfill the destination address, and then specify where do we want to send these funds. So if we build, when we build a transaction, we say, as we said, where the funds are coming from, expecting that this origin transaction has been published. In addition, there are several ways to free the funds. We have pay to public key, play to hash, SegWit, or taproot. And in this case, we choose to use taproot. Why? Because it has two nice properties. One shared with SegWit, that is the witness will not affect the transaction ID, meaning that we can build a transaction without knowing the input that we will give to it afterwards. So we can build a chain of transactions without knowing the actual input that will be given to these transactions. And the second one, taproot, is that we can encode a huge amount of scripts in a transaction without knowing which one of the scripts will be used afterwards to free the funds. So, for example, we can define that the transaction B will use one of 10 scripts without knowing which one will be in the future at the time of signing the transaction. Once we know this, we can build a chain knowing that the transaction B cannot be published until transaction A has been published, and transaction C cannot be published until transaction B has been published. This allows us to create a huge chain of transactions without the need of publishing them. So we can let's say we can block the funds in the transaction A, and then wait an arbitrary amount of time until a counterparty publishes B, even though I already have the transaction C in my power, let's say. And then when another party publishes B, I publish C, and we keep publishing this chain. It's really important to think that we can generate the transactions without actually publishing them. And since these transactions can be signed by an arbitrary amount of people, if these people burn the private key they have used to sign these transactions can no longer be modified, so this becomes a trustless chain. That is not really trustless because we are trusting on the parties burning this private key. Until now, we were talking about a chain that is linear. So basically, we had the transaction A that goes to B and B that goes to C. But we can think in a schema like this one. We can think on two transactions that are input of a new transaction. So when we build this, we say that we cannot publish C until A and B have been published, creating a dependency. This will allow us to, for example, lock the funds in one transaction, that would be transaction C, and then in order to spend these funds, we need the two inputs A and B. And the B could be, for example, the result of BitVMX. Knowing that we have the funds in A, we execute BitVMX in B, and in order to take the funds, you need to win the game in BitVMX. This allows you to create a schema in which the resolution mechanism and the funds are not together. So BitVMX has no real funds on it, and if you win, you can take the funds from anywhere else, from somewhere else, sorry. And then we have this other mechanism. We can think on two transactions that have the same input. So beforehand, we sign these two transactions, and you know that since Bitcoin forbids the double spending, UTXO can only be used once. So if you have transaction B and transaction C, you know that once this transaction A has been published, you'll be able to either publish transaction B or transaction C, which means that de facto what you're doing is you are opening a graph where once transaction A has been published, you choose to follow either the path B or the path C. Once you choose to follow one of the two paths, the other path gets burned. So this is a little representation of what I was explaining, saying that you cannot follow the two paths. You need to choose one of them. So as summary, these connector things allow us to create a directed acyclic graph with dependencies, saying that all the inputs of one transaction need to be published in order to publish another transaction, and mutually exclusive paths. So points where the actor that's publishing these transactions need to choose the path that wants to continue. Keep in mind that here I'm just putting those two outputs, for example, in the mutually exclusive paths, but we could have an arbitrary amount of outputs. The next thing that I want to present is the Winternitz one-time signatures. This is kind of an invention to work around the fact that we don't have a state in Bitcoin. So in all these connectors that we have seen before, we don't have the capacity to pass variables from one script to the other, since Bitcoin has not state. But what we can do is use a little trick and put in the script a public key that encodes a variable, and say that, OK, the actor that will publish this script will have to give a certain value for this public key. And we can say that the only value that he will be able to publish there is one that has been published before. With this schema, we can kind of pass state from one script to the following one since, yeah, sorry?
In BitVM, or Robin is using Lamport signatures, I think, for the same thing. What is the difference between Lamport signatures and Winternitz signatures, and why did you choose to use Winternitz signatures?
Yeah, so they started using Lamport signatures, and now I'm not 100% sure what they are using, because in all the presentation they keep saying that they are using Lamport signatures, but if you look at the repository, they have coded the Winternitz signature. And the point is that, okay, I'll start explaining what Lamport signatures are. I will change this and explain before Lamport, because you are right, it's the kind of the logical initial explanation. So basically, Lamport signatures, you encode a 0 or a 1 with a public key, and you follow the same schema. So basically, you have a seed, so you generate a private key, and then you hash it with an arbitrary hash function. This hashed value will be your public key. So you'll put in the script this public key. Only the owner of the private key, in fact, can give a value that once is hashed, give you this public key. So basically, you'll put the last value in the script, and you will say, OK, give me a value that once is hashed gives this value here. Only the one having the pre-image can publish this. So either you have the pre-image from the beginning, either the counterparty has published the pre-image in another transaction, you go to this transaction, take the value, and put it in your script. So basically, Lamport allows you to just code the 0 or the 1, because you are just hashing one time. Let's say that each public key is encoding just one value, right? But now we can imagine that instead of hashing once, we hash twice, or 3 times, or 4 times. And what you are publishing when you are putting in the script is this last value. And you say, OK, if I give you this, you will hash one time to obtain the last value. That means that this value is the equivalent of the 0, because you have hashed the value plus one time. If I give you this will encode the 1. If I give you this will encode the 2. If I give you this will encode the 3. So with just one public key, instead of encoding just one value, we are able of encoding more than one value. And this has a really nice property that these keys are pretty large. And it may not seem important, but you'll see afterwards in the hands-on, this transaction start being hyper huge. This is, well, I make a spoiler. Since we are in Bitcoin script, this arbitrary hash function 256, but then you think, OK, the SHA-256 is 32 bytes, and the space is really important, so we call the hash 160 that will do the RipMD 160 that will give us a shorter. We do just this to have a shorter key. So if we look at it, I change a little bit the wording. So we don't have hash values and the seed. Suddenly, what we have is the private keys and the public key. So if you want, keep in mind that we have this is the value 0, the 1, the 2, and the 3. So basically, if you want to, for this variable encoded in this public key, you want to say, OK, I will set this variable to the value 2, you will publish this private key. But this has a problem. And the problem is that, OK, if you publish the number 2, it's impossible that I know the number 3, because only you that have the seed private key knows this value. But since we are chaining the hashes, if I publish the number 2, everybody that's looking in the blockchain can compute directly the number 1, the number 0, and the number 0, because the only thing that needs to be done is keep hashing. Then, if I publish this value in one script, and I expect this value to be the same one in the following script that another party will publish, I cannot trust this mechanism anymore unless I put a checksum. So how the checksum works? Let's say that we have two values, because at the end, what we will be doing is encode big hashes. So we'll chunk the hash in parts, and each one of the public keys will encode a certain part of the hash. So we'll have a lot of public keys to encode the whole hash. Let's say that we have these two values, and we publish these two zeros. These two values remain private. So nobody can give neither this value or this value looking at the blockchain. So the checksum will show these two values. So we'll publish this. All the values in the checksum are visible in the blockchain, but only these two values are visible in the blockchain. And the mechanism is like, if we show one more value of this side, we'll show one less value on the other side. So if now we choose this value here, we can compute this just by hashing, but we'll show this one. So this one remains hidden. Again, if in this side we show one more value, we'll show one less value here. So if you keep counting as you do all the combinations, in this schema here, we are encoding, here we have 4 values, here we have 3 values, and there are always 2 hidden values. In this case, there are these 2. We pass one hidden value to the right, another hidden value to the right. If you can keep doing all the combination, you cannot change this value, because then you cannot give a valid checksum, because the hidden values are in the checksum. If you show one more value in the checksum, you will be hiding values in this side. So what you achieved with this mechanism is you found a way of ensuring that once you give a signature, the counterparty cannot change it. You are forced to publish exactly the same thing that has been published, because you don't have the means to change it, because you don't know the seed. So since there are hidden values that you don't know, you don't have the capacity to change it. And if you change one thing that you can change, normally you should show one thing here that you don't know. And with this, we are able to kind of give a state on Bitcoin, because a party can publish one value, we encode this same value with the same public keys in another transaction, and the counterparty publishing this transaction will be forced to publish the same exact value that has been published before. The counterparty will not be able to change the value, but what if this value needs to be presented again from the party that published it the first time? Since this party knows all the private keys, could be able, technically, to change the value. So to work around this, we have 2 possible solutions to avoid it. That is, include a certain path to penalize it. And this is called equivocation. And people, what does is like, in all the chain that I presented before, they put an exit path in such a way that if one party can give 2 values for the same public key, all the funds are slashed. And normally, if I'm a party that don't have the private keys, the only way that I have to publish 2 different values is if the counterparty lied at some point. So they published one value in one script, and for the same public keys, they published a different value. So now I have 2 different values for the same variable. I'm able to slash the funds. Nevertheless, we chose another path, that is, if one counterparty published a value, so let's say in the variable a, one party published a 3, we can reassign this value in a later script in such a way that I present the same value that I had here, and I sign it with one of my keys. So now we have the same value signed with the keys of the two parties, in such a way that the one party will always use the public keys of the counterparty. Since, let's say, actor A and B. A has published the value 3 on the blockchain and has signed it. The actor B presents the same value and signs it with its keys. From that point ongoing, if B needs to use this value, we'll use the public key of A. If A needs to use this value, we'll use the public keys of B. Since you don't have the private keys of the counterparty, you have no means on changing the value. And the last recap concept that are the hashed arrays. And basically, this consists on taking an array of values and keep hashing them one after the other. So if we imagine that we are in an arbitrary step n, what we would do is take the hash of the step n minus 1, take the value n, so let's say the value 3, to put an example, concatenate the previous hash and the current value, and hash this. If we consider that we can only know a hash if we know the pre-image, if we both agree on the value of a certain hash, we can get to the conclusion that we both had the same hash in the previous step and the same value in this position of the array. Keeping that in mind, I repeat this because it's pretty important, agreeing that if we have the same hash for a given step, we know that we had the same hash in the previous step and the same content in this position. And by induction, we can say that we have the same content in all the previous content in this array. And we consider that in this array, we can put transactions, so we can have an array of transactions. We hash all of them one after the other. And if we share the same hash at the end, we can say that the array contains all the same transactions. We can put computation steps or anything that can be vectorized and hashed. Keeping that in mind, what we can do is we take an array of values and we transform this array of values on an array of hashes. And with this array of hashes, we can, if we are not sure of having the same values equal, what we can do is we publish the last hash, and we both look, I publish my hash, and the counterparty will look at this hash. If both hashes are equal, we can say that all the values in the array were equal, right? Just from the property of the thing that we saw before. In case of disagreement, we know, OK, at the beginning, we have the same thing, that's an empty array, and at the end, we have something that's different. So let's find where we diverged. And then you start publishing the intermediate states, saying, for example, in a binary search, you can publish the value that's in the middle. If this hash is equal, we can say that the divergence is in the second part. If it's different, we know that the divergence is in the first part, in such a way that you can start doing a search in such a way that you will end up in one hash that is equal for the two parties, one hash that is different, and then you know that the divergence is in this exact step. We can show this in a graphical way. Let's say that we have 15 steps. This, we could publish the 15 and then do a search in such a way that I say, OK, if you show me 3 values, I'm splitting the space in 4 different intervals, and when you choose one of the intervals, I will show you the values that come afterwards. How we define this This interval is important because if we choose certain lengths, what we'll be doing is, as long as we are choosing one interval or the other, what we'll be doing is choosing the exact step that is different. So imagine now, let's put it as an example, that the step that is different is the number 6. What we'll be doing is, first, we'll publish the 15. The counterparty will publish, will say, OK, the one that's different is the 7. We'll publish the 3 that come afterwards, and then we'll choose the 10 in this order like this. And following the property that I showed you before, if you concatenate 0, 1, 1, 0, in fact, in binary, the number 1, 1, 0 is the number 6. So just by concatenating the choices, you obtain the exact step that is different. And going already for the last part of the presentation, now let's imagine that you build an emulator of, for example, RISC-V. You execute a compiled program, and at each one of the steps, you are able to extract this information of each one of the instructions. In such case, you can take all this information, hash it together, get to the end, compare if the 2 hashes are equal, and if 2 hashes are equal, you can say that an arbitrary execution was exactly the same in 2 counterparties that executed this in 2 different computers and without any connection between them. In fact, if we consider that we start the execution with an empty machine, you don't need to hash all the read values because at each time, the only thing that's modifying the state of the machine are the outputs, that are the ones that are modifying the state of the memory. So what you can do is just keep hashing the output values as long as the execution keeps going. So I recap and I come back to this previous slide where we had these values and we transform the values array to the hashed array. So now what you can do is have this execution, you put all the output values in the values array, you generate the hashed array, and with this hashed array, you can perform an NARI search to find which is the exact step that gives you a different hash. And once you know which is the step, you can ask to the party you can ask to one of the parties to say, OK, now we have a hash that is correct and a hash that is incorrect. Show the content of the middle. And once the content in the middle is being shown, that is basically all these values here, you have different sources of discrepancy. The first one, the hash computation challenge. So if one counterparty shows the content in the middle and the previous hash was equal, we have exactly the same values here, but the hash is different. What is wrong is the hash. What you can do is, on-chain, you compute the hash, and you demonstrate that the hash computation was not correct. And then you slice the funds. Imagine that you compute the hash, but the hash is correct. What is incorrect are the outputs. So what you'll need to do here is execute this RISC-V command on chain. You don't need to run the whole computation of the 4 billion steps. You only need to run one single instruction to demonstrate the disagreement. And then if you execute this on chain and you prove that the outputs that have been given by one of the parties are incorrect, just by executing this on chain, you can prove that the execution was incorrect. And we'll call this challenge execution challenge. Then remember that we had this hash that was correct, this hash that was incorrect. Let's say that you look at the information that has been published, and what is different is the program counter. Considering that the program counter is being written here, you can ask the counterparty, OK, give me the previous hash and the outputs that give this hash. Since this hash was the same for the two of us, the previous program counter should be exactly the same, since you need to know the pre-image. So basically, the counterparty will not be able to give you a previous hash and a program counter that hashed give the correct hash, being the program counter different from what you have. So basically, he's lying, and since he will not be able to present this, you slash the funds. Last but not least, the most difficult challenge, that is the read value challenge. So imagine that the lie is indeed in the read value. If you remember it, we are only hashing the right values. We don't have any memory in all this. In the paper of BitVM, they had all the memory in a Merkle tree, so they need to compute it each time. Here, we have not talked about memory until now, and indeed, there is no memory in BitVMX. The trick that's done here is that we consider that we know the state of the memory at the beginning. At the beginning, the memory is empty. So if we are reading a certain value from a certain address, it's either because it has the initial value, so 0, or it has been modified before. And if it has been modified before, since we have agreed on all the writes that has been done until one point in the array, we can go to the point where this value has been written and verify which value has been written at this exact step. So once this is done, there are two possibilities. And we used this last step kind of to be able to do this. Let's say that one party says, the party that's publishing this, says this position of memory has this value because the last time that was written was in this step. There are two possibilities here, that the published last step is greater than the last step. If it's greater, that means that the address that will be written in this published last step will be a different address as the one that has been published. The only thing that we need to do here is go to this published last step and verify that indeed the address that's being written is a different one than the one that's being published here. What if the published step is smaller than the real one? What we can do is go to the real last step, show that this last step is greater than the published one, and it's writing in the address that has been published, meaning that indeed the counterparty was lying in this last step, because we are able to prove that there is a write in a last step that's bigger of the one published that contains the same address. And if you look at it, we have been able to take an execution, compute a hash, see where we had a discrepancy in this execution, and force one party to show all the information regarding this exact step, and then be able to check all the values that have been published. So either the values were correct, either we have a way to counterprove it. So making a little bit of summary, these are all the possible lies that one of the counterparties can say. There are these two at the end that I didn't mention, that basically at the beginning of the computation, the party that's publishing the hash also publishes the step at which the computation will end. And you can just check this going to this step and verifying that the program is ending. And the input value challenge, that's we're working on it, and it's basically the one that will, when you publish the result of the execution, you'll publish also the input that makes this program end up in a good manner. So basically, here what will be done is you'll have the snark verifier. The input will be the input that makes this verifier end up in true. And how do we build all this? If you remember it, we had all these transactions that have been pre-signed in such a way that we have all these publications. We reach a point. You need to choose a challenge following the connector schema that we had at the beginning. So what happens is you have these two parties, and the two parties generate all the public keys for the whole protocol, and they exchange them through the network. And here we'll talk about prover and verifier. The prover will be the one that locks the funds somewhere, and once he's able to give some proof to these funds, he will free the funds afterwards. The verifier will be the one that will be looking. If the proof that is presented is wrong, basically, will challenge the prover and slash the funds, or whatever mechanism you put in the bridge design or rollup, wherever. Keeping in mind that the verification system and the more complicated schema where you are using are detached from the thing that we said before, that this will just give you who's right or who's not right. So they exchange the public keys, and then the one that will lock the funds will sign all the transactions and will send all the signatures to the counterparty. The counterparty will generate all the transactions and will check that all the signatures are correct. If all the signatures are correct, say, OK, I have the same exact protocol, I sign everything, and I send my signatures to the counterparty. At this point, the prover has generated all the transactions and has all its signatures and the signatures of the counterparty. Since you have all the signatures of the counterparty, you are sure that you'll be able to publish all the messages. Since you are sure that you'll be able to do this, you trust kind of the configuration, and then and only then you lock the funds in the final address. Just in the moment, you'll be sure that you can end up the protocol correctly. I hope you, this has been a little bit intense. And now let's pass to a more calm part of the talk. Thanks to stay with me until here. So let's hope that we don't have the live effect, the demo effect today, and that everything works. So basically here we have two microservices that are running in my laptop, but this could be running in AWS or wherever. Everything is fully Dockerized, blah, blah, blah. And we have the prover here and the verifier here. If we come here, we have a Swagger, and basically we only have two calls. This one that will generate all the setup following the thing that I told before. So the prover will generate all the public keys, will send them to the, well, I will explain it as it happens because it takes a little bit. The only thing that you need to configure beforehand, is how many bits you will use to perform the search, and how many steps will have the computation. So in here, we are just doing a toy computation because the big computation take more to generate all the tree. We'll say that we have 1,000 steps, and we'll use 2 bits to choose to separate the wrong hashes, meaning that at each time, we'll separate the search space in 4 intervals. So now, if I click here, what just happened is that we'll start seeing that these two are talking one to the other, and things that start passing. And basically, the prover will send all the public keys to the verifier. The verifier will take these public keys, and with these public keys, you are already able to generate all the transactions, putting in each one of the transactions the values that you need. So this is happening. Now we see that the public keys have been correctly generated. The public keys now are sent back to the prover. The prover will take these public keys, will generate the whole tree of transactions, and will start signing all the transactions with its private key. Once this is done, he will send all the signatures to the verifier that will take all the transactions generated with the public keys that have received before and check that the signatures are correct. Keep in mind that since we are just sending the signatures and not the private key, the whole graph cannot be changed unless all the parties collide, because each one of the transactions is signed by the private key of all the parties. So now we see that the signatures endpoint is 200. It has responded here. So luckily, yeah, we have the setup fund 200. So if we come, this was interacting with Mutinynet network that, for those who don't know it, it's a super cool network to make demos and development, because it's just a regular Bitcoin network, but with a confirmation time of 30 seconds and a faucet that allows you to ask as many Bitcoins as you want. Because even in testnet, it's pretty tough to get testnet BTC. And if you want to have these kind of things live, it's not really easy. So if now we refresh, you see that the network that's not really being used. So we see one transaction here, 2, 1, 1, 2. What happened here is that in this transaction, I took funds from the faucet. And is this transaction here. So what I've done is I went to the faucet and took these BTCs and logged them in an address that's controlled by the prover. Then all this protocol started at this point here. And here, the setup phase ended up, meaning that, OK, at this point, we agreed on all these transaction signatures, blah, blah. So the prover is sure that he can actually log the funds in the address containing the protocol. And this is this transference here. We only log the funds once we know that everything is correct. We don't need to log them before. And now, for those who want to share it, this website here, BitVMX-explorer.com, I did this to make things a little bit easier. So if we come here and we copy this transaction here, we are in Mutinynet, but we see this. So basically, this is the legend. The yellow stands for the funding transaction, the green for the transaction published by the prover, and the blue for the transaction published by the verifier. We only see the funding transaction because it's the only thing that we have done. And now, what we can say is that, OK, this setup that we have done now has this identifier. And there's another endpoint. It's pretty simple. What we are doing here is we are saying to the prover, OK, now trigger the protocol. And if the two parties are not malicious and are executing everything well, this has no sense because they will publish the last hash. The last hash will be exactly the same, and the protocol will not be triggered. And I'm doing a super small computation. It's like I take advantage to come here. If you come here, here there are 3 articles super interesting from Martin Jonas. That's the guy that has led the implementation of the emulator. And he has done an example script with kind of the more tough executions that you can have, like a read that is not aligned in C++, so he could test the emulator, but it's a super toy execution that's doing nothing, basically. But that has these things of, OK, what happens if you are trying to read a position in memory that is not aligned and it's taking 2 of them? This allowed him to kind of proof test that the emulator is working correctly.
You chose the worst case of the emulator and tested here.
Exactly, yeah. But it's super short. When we executed the snark verification, it was 4 billion of steps. Here, it's 1,000. The order of magnitude is much smaller. And OK, what I was saying is that if both parties say the same, there will be no triggering of the protocol. So what I've done is, in the code, you can tell to one of the parties, OK, you will lie in this step, and the kind of lie that you'll make is of this kind. So if you look here, what's set up now is that the verifier will lie in the step 345, and the kind of lie that he will publish is that when executing the code, he will make a wrong execution. So he will put in the output something that's wrong. And considering this, we can come here, just verify. Let me verify that I copied this. So keep in mind that now we'll trigger the protocol, and the verifier will lie in the execution step. So now we call this, and if we come to Mutinynet, what happened is that the prover executed everything, computed the hash, the verifier saw that the prover has published the hash, and did the execution and verified that the hashes are different. And if we see here, we're starting to have a lot of transactions that contain all the things that I have been explaining before. So if we come here and we now refresh, we start having all these transactions. And if we look here, this is the raw witness. And if we look at it, we have basically, this is the value that is being published. And this is the Winternitz key that encodes this value. So we have the encoding on all these hashes following the Winternitz that we just explained before. And I just did this, so that takes the raw input and simplifies it. So what we are doing here is, in the first transaction, we are publishing the hash result. In here, the verifier just executes everything and says, OK, I don't trust you. So now, show me intermediate states. So now we'll start showing these 3 hashes, because if you remember it, we put 2 bytes to make the choice. So since we have the last value and the first one, in order to divide by 4 the search space, we need to publish 3 values. And from now on, we have these 3 values. We choose which interval we want to follow. Then the prover will publish 3 values. And since we need this choice afterwards, here what we are doing is the cross signature that I was explaining before. So in order to show it, I have taken all the public keys that are being used, I concatenate them, and I hash them together. And I put the value here. So basically, you can see that this 01 has been published with 1 keys that has start by C01. These are the Winternitz keys from the verifier. And here we have the same exact thing, C01. So this 01 is published with the keys from the verifier, but this 01 is published with the keys of the prover. Since the script checks that these two values must be equal, the prover can only publish the same exact value that has been published before. And this is how we are able to pass this O1 from one script to the other and force this party to publish this exact value. Now, if we continue going, you'll see all the time that is one choice, some hashes, one choice, some hashes. And luckily, this has already ended. Yeah. So I will refresh it. And you can come here. This is because I know it. At this step is the last choice. And basically here we are forcing the party to publish all the values that I was talking before. These are the, if you remember it, we had this read address value, read 1 address value, read 2 address value, and we had the values that are written, and we have here all these values decomposed following the Winternitz codification. Then the verifier says, OK, looks. In this step here, what will happen is that the verifier looks at the trace that has been published and says, OK, this is not correct, but for which reason? And here, what's being done is detect that the execution was not correct. So there's a tree of transactions. The verifier is choosing the execution path. And then the prover can come here and publish this, that will actually perform a RISC-V execution on chain. If we come here to the code, this is the execution of this exact instruction on chain.
How many kilobytes was that?
Yeah, 11.
11 kilobytes.
Yeah, it's here. Yeah, it's super small, indeed. And that's a little bit all. Just one thing, last thing to show kind of graphically how these Winternitz signatures work. And so this is what is being published in the witness. So if we take this, this corresponds to the value 3. And this is the maximum amount of values that we are encoding. So if we open, I just go like this, and we run it once, and we take this. This is the public key that is in the script. If we copy this, and we go to the code, and we look for it, we have indeed this. So what the script does is it takes this value, it hashes it, and verifies that in this position of the hashing, there's this key here. And we can see, because now we did it just once, so we said the maximum is 4. For the 0 will be the same exact thing. The only thing is that now we need to hash it 1, 2, 3, 4. And if we come to this 4, we come to the code, bingo, we have it again. So this is how Winternitz works. And that's all on my side. I don't know if you have any question. Thanks for staying until now and not fall asleep.
Well, thank you very much, Ramon. This was very ambitious and very broad. According to the schedule, you're supposed to go for 30 minutes and have a 30-minute break, but it seems like you went for 1 hour, and that was very impressive. So thank you for this. I feel like I've learned something new. I have to really compare these signatures with Lamport, which seem to have been very much promoted. Actually, yeah, you could provide an explanation why these signatures were used instead of Lamport. I know that Veronica asked you the same question and she went out, but maybe for the people watching on live stream.
basically the Lamport are the Winternitz with just one hash. So instead, here we were encoding 4 values in one public key. In the example that I just shown here, that I was hashing it 4 times. If one public key only encodes one value, this is equal to the Lamport. So you would have one public key for the 0, one public key for the 1, one public key for the 2, one public key for the 3. This basically allows you to optimize the space, but the key idea is exactly the same.
So the only question is at this point, where can people read more about this and maybe find a more succinct explanation of everything?
If you go to, well, there's the BitVMX website. You can go to the Explorer, and in the Explorer you'll find here the demo that we did when we published this on mainnet, the white paper where all that I explained is explained better, let's say, in a more academic way. And these articles that we are writing, where we are basically explaining all these pieces, but isolated in articles, so it's more affordable for a reader, because having everything at once can be a little bit intense. So it's like one article for Winternitz, one article for the challenges, one article for everything. And once you have this, if you come to protocol and you erase this, we have loaded some examples, so you can see how an execution challenge looks like. You click here, and you will have a trace, how a hash challenge looks like, and you have the trace. And right, with the paper in one side and this on the other, you should be able to more or less follow what's happening in the blockchain.
Well, Janus is up next, but he's getting mic'd right now, so I'll ask you another question. I guess there are people watching this and wondering, what is the point of it? How can the average user make use of what you presented to build something? And what would be some potential use cases?
So for me, the cool part of it is that you can run every compiled program, so you can build a rollup in Rust instead of making everything on a snark, blah, blah. So everything that you can build in a compilable program, you can run it here. For me, it's the main advantage regarding BitVM2, that you really need to get into the snarks, and everything is coded in Bitcoin script, which is pretty heavy and pretty difficult. In here, you can have everything in Rust or C++, compile it, and have it on Bitcoin. So you could build everything that you imagine in a compilable programming language and use our framework.
All right, thank you very much.
I think.
Round of applause for Ramon once again.